Okay, so today we're finishing up 3.1 about exponential functions and their graphs. We're looking today at the base, the natural base of e. It's called the natural exponent function. E is an irrational number. It has a value. E is not a letter in this case, it is a value. It is a value like pi has a value. It's called the natural exponential function. We're going to evaluate a couple of these. You will need your calculators to do this. F of negative 2 is e to the negative 2. You put that into your calculator and you'll get approximately 0.135. If I evaluate f of 0.25, it's e to the 0.25, approximately 1.284. Notice I'm rounding it out to 3 decimal places. If I do the same thing for b here, f of negative 2, it's 2 times e to the 0.025 times negative 2. I put that in my calculator, and it will equal approximately 1.213. Do the same thing with 0.25. 2 times e, 0.025 times 0.25. Put all that information into my calculator, and await it. I may have put this information in my calculator wrong. Just a second. Okay, instead of going back, I did put it into my calculator wrong. Instead of going back and changing the entire problem, we're going to use e to the 0.25, e to the 0.25. So we'll be changing the problem instead of 0.025, 0.25x. I apologize. Okay, so then I put this into my calculator and you get 2.129. How do I graph these? You graph them the exact same way. Okay? 5 times e to the 0.17x. Okay? It has no horizontal shift. It's an exponential function. So my asymptote is at y equals 0. I'm going to plug in the same values of 0 and 1. 5 times e to the 0.17 is 0. 5 times e to the 0. E to the 0 is 1. So that's 5. If I plug in 1 times e to the 0.17 times 1, I'm going to get 5.927. Again, we can only sketch these because they are not going to be accurate. So it's 0, 5, and 1, and 5.927, not quite 6. And we have an exponential graph that goes like that. Again, my domain is all real numbers. And my range is y is greater than 0. They graph the exact same way. The second one, again, I'm going to use the points 0 and 1 and plug it into my function. One half times e to the negative point times e, not to the e power, e to the negative 0.58 times 0, which is e to the 0, which is 1 times 1 half. Do the same thing for 1. Let's plug that all into my calculator and I get approximately a 0.28. Again, I have no shift, so my horizontal asymptote is at y equals 0. Now let's plot 0, 1 half, and 1.28 below that half mark, which isn't quite. And there we go. So my domain, all real numbers. My range, again, will be y greater than 0. Let's talk about the shifts. They identify the shifts and the asymptotes. You use it exactly the same way as any other exponential function. So if I'm looking at this reflection, it's reflected in the x. It's going to go left 2, down 1. My horizontal asymptote is at y equals -1, which also defines my range. Okay, so here now I have it reflected in the y. It's going to go left 2 also, but it's going to go up 4, and my horizontal asymptote is at y equals 4. Okay, the e and exponential functions have a lot to do with compounding interest, which is banking. It says the balance A, so we're defining our variables, in an account after T number of years with principal P. Principal is the amount invested. Amount invested. And an annual interest rate. You have to change your percentage to decimal form given by the following formulas. For in compounding, that's how many times they're calculating the interest. Like quarterly would be 4 times a year. Daily, 365 days a year. Monthly, 12 times a year. For continuous compounding, it's a different formula. You still have your amount, your principal, but your base is E. So the R times T. Let's look at one example. A total of $4,000 is invested at an annual interest rate. So let's identify our variables. Amount invested is our principal. Annual interest rate. Remember, we got to make that a decimal. So it's 0.0525. Find the balance in the account after 6 years. So T equal 6. When I go to part A here, compounded quarterly, it doesn't say continuously, so I use the first formula. The amount is $4,000, my principal, times 1 plus my interest rate. Quarterly is 4. I put all this into my calculator, and my amount will be $5,000, after 6 years, $5,469.82. What if it's compounded monthly? Let's see if there's a big difference. So here my n is equal to 4. Here my n is equal to 12. A equal 4,000 times 1, 2, 5. Put all of this into my calculator and I get an amount of approximately $5,477.27. What if it's compounded daily? Now my n changes. My n changes to 365. Divide by 365. Put all of that into my calculator and I get approximately $5,480.91. Well, there's one more. What if it's compounded continuously? If it's compounded continuously, we use the other formula. We use this formula. So my amount is 4,000 times E, the rate, times T, the number of years. Plug that into my calculator, and we get $5,481.91.